Welcome, welcome to this webinar about Physical Science Lesson 4, which is chemistry. In this lesson, we're going to go over some of the harder concepts in the class and do a few practice problems. So we don't have time to go over everything, but hopefully it will be enough to help you with some of your test. And if you are watching the webinar live, you can ask questions with the chat feature on GoToWebinar. Or if you are watching the recording later, then you can certainly send questions by email or call your teacher. So we're going to start with Lesson 4, Assignment 1, the classification of matter. So first, the difference between a few different terms that we use in chemistry. So chemical changes happen when we rearrange the molecules of a substance to create a new substance. An example of this would be lighting something on fire. So you've taken something like a match and converted it into ashes and smoke, and you've released light and heat. So we took something and changed it into something else with different molecules, different properties. That's a chemical change. And a physical change, by contrast, doesn't rearrange the molecules. So an example of that would just be something like breaking a material. So now you have two different pieces, they're a different shape, but you haven't made it into anything new. If you have a piece of paper and you cut it, you just have smaller pieces of paper. You didn't make a new substance. And some more examples of the properties would be chemical properties are only seen when the substance reacts, but physical properties are present all the time. And for example, color is a physical property. It always has a color, but flammability is a chemical property. So wood and paper and fuel could just sit there for years and not really be doing anything, but when they start to react, you can see that they have that physical property of being flammable. Compounds and mixtures are different. Compounds are when you have molecules that are chemically combined. So they've made a new molecule, they can't be separated without another chemical reaction happening. And these new molecules lose the original properties of their atoms and gain new properties. Mixtures are different though. Mixtures are physically mixed, like in this bright jar over here, where they haven't bonded together and made new molecules. They're just physically in the same area, mixed up. The atoms all keep their original molecules, or I'm sorry, they keep their original properties, and they could be separated without a chemical reaction to separate them. Some things from assignment 2 where we learn about atoms and molecules. So if we look at the periodic table, each element has some numbers with it. So the most important one is the atomic number, and that's the number that it has on the periodic table. So they're ordered in number, and they're ordered by their atomic number. And that's the number of protons in the atom. Atomic number never changes. It defines the element. So you can see oxygen in the top left here is number 8. That means it has 8 protons. And oxygen will always have 8 protons. If you had something with 7 protons or something with 9 protons, it wouldn't be oxygen anymore. It would be a different element. So atomic number is very important. It also happens to tell us the number of electrons that would be in a neutral atom, because atoms would have the same number of protons and electrons if they're neutral. So oxygen, in its normal neutral state, would have 8 electrons. Another important number would be the atomic mass, and that's listed underneath the element on the periodic table. And this includes the mass of the protons and neutrons and electrons all together. And it is measured in a unit called atomic mass units, which is abbreviated AMU, or sometimes just abbreviated U. You can use the atomic mass to find the molecular mass of a compound. So, for example, you have water. Water is made up of 1 oxygen and 2 hydrogens. And the atomic mass of oxygen is 15.9 AMU, and hydrogen are each 1.0. So when you add the 3 of them together, 15.9 plus 1.0 plus 1.0 gives us 17.9. So the total molecular mass for a water molecule is 17.9 AMU. When we get into assignment 3, we start talking about fundamental laws of chemistry, talking about things that will affect the way that atoms combine. So the first thing is valence. So valence electrons are the electrons in the outer electron shell. So this is a simplified version of what an atom looks like, but it's the model that we usually use in chemistry, just to help explain what's going on with the electrons. So you have the nucleus in the middle, which is protons and neutrons, and then you have your electrons. And they're arranged in energy levels that we sometimes call shells. And you can have different numbers of electrons in each shell. So the ones that really matter are the ones on the outside, because those are the ones that can react with other things. So if this atom bumps into another atom, the electrons in the middle aren't going to do anything. It's the ones on the outside that will react. So those are called valence electrons. And those are very important. The other way that valence is used is to describe the number of electrons that an atom needs to give or take in order to have a complete outer shell. So you learn when you look about the structure of the atoms that the first shell can have 2 electrons, and the second and third shells could each have 8 electrons. So this example, we have fluorine, which has 7 electrons in its outside shell. It wants one more. It wants to fill it up. It wants to have 8. So because fluorine is lacking 1, it only needs 1 more to fill up that shell, we say it has a valence of -1. Okay, so because it's got this one spot here with no electron, it's got a valence of -1. By contrast, we can also look at sodium, which has kind of an extra electron hanging out here. So it's got a full first shell, it's got 2. Its second shell has 8, so that one's full. And then it started trying to make a third shell, but it's only got 1. So instead of getting 7 more electrons to fill this up, it's actually going to be easier for sodium to just get rid of this electron. And then it becomes a sodium that only has 2 shells, and the outer one will be this second shell, and that's full. So if it just kind of gets rid of this extra one, then it's got a full outer shell to work with, so it's happier that way. So sodium, the best thing it can do is get rid of 1 electron, so that gives it a valence of +1, because it has 1 extra that it wants to get rid of. So fluorine has valence of -1 because it needs 1. Sodium is +1 because it needs to get rid of 1. Usually metals have a positive valence and most nonmetals have a negative valence. So you can kind of keep that in mind as you're trying to figure out which is which. Now, this matters when we're trying to figure out molecular formulas. So formulas show how many of each type of atom is in a molecule. So water, again, water molecules are H2O. So that's their formula is H2O. It's 2 hydrogens, H2, and 1 oxygen, it's O. So when we're trying to make formulas, the valences have to balance each other. So for example, you've got calcium, which has a valence of +2. So how do we know this? We would look at the periodic table. We would figure out how many valence electrons calcium has. Calcium has 2 extras that it needs to get rid of. Chlorine has a valence of -1. So calcium and chlorine are bonding. 2 chlorine atoms need to balance out 1 calcium atom. Okay, calcium is +2, chlorine is -1. So we need to balance them. We need the -1s to balance out the +2s. So that means we just need to have 2 chlorines for every calcium. So the formula gets written like this: chlorine with a little 2, that's called a subscript, and calcium. And we don't write anything here. You could technically write calcium with a little 1 and say that's our subscript is 1, but they don't do that. If you just see one with no letter or no number as a subscript, it just means that there's only 1 there. Whoops. Okay, so when you're balancing formulas, you want to just use those valences to determine how many will bond to another element. when you're doing this, you can write the valences to kind of help you balance it, and then those can go away when you're done. So for example, you've got magnesium, which has a valence of +2, and chlorine, which has a valence of -1. So you've got 2 here, you've got -1 here, so you're going to need twice as many of these twice as many as the chlorines to balance out the magnesium. So you're going to form magnesium chloride, and you put a subscript 2 to tell us that we have 2 chlorines for the magnesium. Okay, and here in purple I have the valences, but when you're all done and you want to write the formula efficiently, you get rid of those. You need this too, though, because that's telling us how many chlorines do we need. So our final formula is this: magnesium chloride, and it tells us that for every 1 magnesium, we have 2 chlorine atoms, because the valences have to balance out. Okay. All right, I don't know why it's keeping the red pen. Sorry. Oh, well, there it goes. Okay. When you're going to balance the formulas, an easy trick to do this, as long as you only have 2 atoms, is write the valence for the second atom as the subscript for the first atom, and write the valence for the first atom as the subscript for the second atom. So what does that mean? So we have aluminum, which has a valence of 2, and oxygen, which has a valence of +3. So aluminum has a valence of -2, so we're going to write 2 as the subscript for oxygen. So I kind of got it color-coded over here in this part. Oh gosh. So aluminum is -2, oxygen is 2. And oxygen has a valence of 3, so we're going to give aluminum a valence of, or a subscript of 3. All right, so all we're doing is taking the number from the valence of aluminum and putting it as a subscript for oxygen, the valence of oxygen, and put that number as a subscript for aluminum. Now, why in the world would we do that? It's just the easiest way to work out the math. So in both of these cases, our charges is going to balance out and be 6 and 6. So they're now balanced with -6 on aluminum being balanced by the +6 on oxygen. So aluminum has a valence of -2. If we have 3 aluminum atoms, then our total valence happening here is going to be -6. And oxygen has a valence of +3, but if we have 2 oxygen atoms, then the total valence going on there is going to be +6. Okay, so -6 and +6 balance out. So that's just a way to kind of balance out the formulas for a molecule. Once you have balanced out the formula, you can't change the subscripts. So if you have aluminum 3, oxygen 2, you can't go changing that and making that aluminum 4 or oxygen 1. It's got to stay the way it is. So now when you're going to do chemical equations, we're going to take one molecule plus one molecule as your reactants, and that's going to give you some molecules as your product. You can't change the subscripts. You got to stick with the molecules you're working with. So the only thing you can change to get different numbers is going to be what we call coefficients. So coefficients are numbers that go before the molecule. So for example, if you have aluminum oxide with aluminum 3, oxygen 2, there's 3 aluminum atoms and 2 oxygen atoms. So again, you can't change that proportion. So if you need more oxygens or you need more aluminums, you have to use a subscript. So if you put 2 Al3O2, put a 2 here, that's called a coefficient, and that's going to multiply everything in this formula by 2. So now we have 2 aluminum oxide, so you have 2 Al3, so that tells us that there's 2 of whatever's here. So you've got 3 aluminums times 2, it's going to give us 6 total aluminums. And you got 2 oxygen 2s, so 2 times 2 gives you 4, so you got 4 oxygen atoms. Okay, so this is going to help you, knowing this, figure out how to balance equations. To balance equations, you kind of have to figure out how many molecules of the reactant will there be, and how many molecules of the product will there be. Okay, so I'm going to switch over to this website, all right, from Colorado University, and it's got this great tool to show us how to balance reactions. So in this reaction, on the left side is our reactants, the things that start the reaction, and on the right side over here are the products, which are what we get in the end. And our reaction's written down here. So we're going to take nitrogen 2 and hydrogen, just 2 molecules of hydrogen together, and we're going to get ammonia, which is NH3. So if we try to do that and we just say, well, let's take one of each, one of those, and that gives us one of these. It doesn't quite work out. So you can see on the bottom, you have N2 and you have H2. We can't change these subscript numbers at all. So no matter what, we've got 2 nitrogens and we have 2 hydrogens. Over here, though, we're ending up with 3 hydrogens and 1 nitrogen. So this doesn't work. This is not balanced. And they've got it broken down here so you can look at each molecule and see if it's, or each atom and see if it's balanced. So on our nitrogen, we have this balance here, and the left side is our reactants, and the right side is our products. So you can see our nitrogen isn't balanced. We're starting out with 2 nitrogens, and we only get 1 the way we have it set up. So what can we change? Well, we can't get rid of nitrogens on the left. It seems like, oh, well, just remove one of these, right? But remember, our formula is N2. So that means we're stuck with 2 nitrogens. We can't get rid of just 1. If we try to get rid of 1, they both go away. So we can't do that. So our way to balance this out, we're going to obviously have to add more on the right. So if I add more to the reactant, okay, now our nitrogens are balanced out. We start out with 2 nitrogens, we end up with 2 nitrogens. That's pretty good. Now our hydrogens have gotten very unbalanced. So same thing, we've got hydrogen. The left side of the balance is our reactants, and the right side is our products. So we're starting out with 2 hydrogens and ending up with 6. That's not going to work. So how do we get that balanced? Well, we can't get rid of any of these from the 6 side because this is our formula, NH3. If we get rid of any of these hydrogens, then we're also getting rid of nitrogen. We just balance those out, so we don't want to do that. So our other option is to go back here to the reactants and add some more. So let's make them balanced. Okay, still not balanced. And now we're balanced. Okay, so now we've balanced everything out. All of our nitrogens are balanced, all of our hydrogens are balanced, and we can count down here. We have 1 nitrogen 2, so that means we're starting out with 2 nitrogens in our products, or our reactants. If we go over to our products, we have 2 nitrogens. All right, cool. And then let's look at our hydrogens. We have 3 H2, so that gives us a total of 6 hydrogens. And over here we have 2, we have H3. 2 times 3 still gives us 6. Okay, so it took a couple of steps. We had to figure out how to balance one without throwing off the other. But that's what this is all about. You can't have atoms disappear or atoms come out of nowhere. So you need to start with the same number of nitrogens you end with. You need to start with the same number of hydrogens you end with. Okay, so let's look at another example of this from your study guide, your study unit. So this example is zinc and hydrochloric acid. So if we look at this, we're starting with a Zn and we're starting with an HCl and we're ending with zinc chloride, ZnCl2, and some free hydrogen ions. So let's just look at each molecule. We've got 3 different atoms involved here. So in this case, is the zinc balanced? Well, yes, the zinc is. We start out with 1 and we end up with 1. All right. How about is the hydrogen balanced? We start out with 1, we end up with 1. So far, so good. The chlorine, though, is a chlorine balance. So we start out with 1, we end up with 2. So no, chlorine's not balanced. So what can we do? So again, we can't get rid of this chlorine here. We can't change the subscript. We have Cl2. It's going to be a 2. You can't make it a 1. So we're going to have to go over here and add another one of these HCl molecules so that we start out with 2 chlorines and we end up with 2 chlorines. So let's do that. So now we have 2 HCl. Okay, so now our chlorines are balanced. We have 2 Cl's over here and we have Cl2, just 2 Cl's over here. but now we've gone and screwed up the hydrogen. Okay, now we have two hydrogens here and only one over here. So fortunately, this hydrogen ions are just hanging out by themselves, so it's easy enough to fix that without screwing anything else up. We just add another coefficient to that hydrogen, and now we have two. So let's check through everything else. The zinc is still balanced, 1 and 1. Our hydrogen, we have 2 in the reactants, and we have 2 in the products. And chlorine, we have 1 in the reactants. I'm sorry, we have 2 in the reactants, and we have 2 in the products. Okay, so we've balanced that reaction. Another thing you may be asked to do is to find a percentage composition of a molecule. So what does that mean? You're finding out if you have a molecule made up of different atoms, how much of the molecule is a certain atom? What percentage of the molecule is made up of that atom? So a couple steps to do that. The first step is calculate the molecular mass of the compound. So we're going to just, as an example, use water. We've got H2O. So we got color coding here. Our red is hydrogen, our purple is oxygen. So we're going to add up the molecular mass. I'm sorry, we're going to add up all of the atomic masses to find the total molecular mass. So these atomic masses are on the periodic table. So your mass for oxygen is 15.9, and your mass for hydrogen is 1.0, so that makes our total 17.9. Now, we want to find out, in this example, how much of that water molecule is made up of hydrogen? What percentage of the mass is made of hydrogen? So we're going to remember this number, 17.9 is the total, but we're going to look at hydrogen. The atomic mass of hydrogen is 1.0, and there's 2 hydrogens in the molecule for water. So 1 times 2 gives us 2. All right, so that's pretty simple. And we divide that number by the molecular mass. So 2 divided by our total molecular mass, which is 17, gives us 0.111. All right, so that's almost our final answer, but remember we want it to be a percentage. So to turn a decimal into a percent, we just multiply it by 100. So our answer is 11.1. So in every water molecule, 11.1% of the mass is hydrogen. The rest is oxygen. So let's do another example. This is one from your text on page 49. It's a work it out problem. They give us an example of calcium chloride, and they want to know what percentage of it is chlorine. So the molecular mass of the whole compound is the sum of the atomic masses of all the atoms in it. So we have calcium, which is 40.0, chlorine, which is 35.4, chlorine, which is 35.4. Our total molecular mass, if you add the 3 of those, is 110.98. So that's step 1. What's our total? Step 2, okay, we're dealing with chlorine. So how much of it is chlorine? Well, chlorine is in there twice. Its mass is 35.45. We have 2 of those, so the total mass of chlorine is 70.9. So we're going to take the mass of chlorine divided by our total molecular mass, which gives us 0.63. And then again, we just need to turn that answer into a percentage. To do that, we multiply by 100, and we get 63%. Okay, so that's how to find percent composition. And if we go into assignment 6 and 7, I kind of combined these because it talks about metals, nonmetals, acids, and bases, and salts in 6. And 7, it talks about ionization, and then goes back to some things related to acids and bases. So I just kind of threw them all together. So let's talk about what an ion is first. So when an atom loses an electron, it's left with a positive charge, and it's called a cation. This one on the left lost an electron. The one on the right gained an extra electron, so now it's called an anion. So cations have lost an electron. Remember, electrons are negative, so if they lost something negative, they've become positive. So cations are positive. Anions have gained an extra negative charge, so they're negative. Okay, so that's all an ion is. And we're going to talk about acids and bases and how they're related to ions. So acids contain a hydrogen that can be replaced by a metal. So it's kind of a weird definition, but it's a molecule that has a hydrogen atom in it, where if you put that molecule in water and you put some metal ions in water, the metal is going to replace the hydrogen. That's how we define acid. When that happens, though, it releases that hydrogen ion into the solution. So that's what's going to be kind of important. So when that happens, acids just release hydrogen ions. There's just H's floating all over the place. Also important to know is once that substitution happens, where the metal comes in and replaces it, you've got your acid here. SN is a metal listed. It comes in and replaces the hydrogen, and it makes a molecule that we call a salt. So a salt happens when you replace the hydrogen in an acid with a metal, you get this new compound, and that's called a salt. And then it also makes all these free-floating hydrogens. A base is a compound that breaks apart in water to give off a hydroxide ion, which is OH. So OH is hydroxide or hydroxyl. So when you put them in water, acids release hydrogen, bases release OH. Another important word is alkali. That just means it's a pretty strong base. So we'll talk about strong and weak. On the pH scale, 7 is neutral, and lower than that is acids, and the further you get away from neutral, the stronger it gets. And higher than 7 is bases. So these couple are weak, and the further you get away from 7, the stronger the base. There's different indicators, which are chemicals that you could use to find pH, so they would change color. So the kind of famous one would be litmus paper. If you put litmus paper in the solution, if it's an acid, it will turn red. If it's a base, it will turn blue. There's other indicators that change to other colors to indicate how strong the acid or base is. And when we talk about strength, what do we mean? Well, strong acids or bases ionize completely, and weak acids and bases do not. So that's how we define that. And when they do ionize, you've got acids that release hydrogen ions, bases that release hydroxyl ions. So these are kind of the things that give them their properties. So you have these free ions floating around, and those can actually just combine with each other and create normal water molecules. And water is neutral. So when the ions are removed in this way, you've got the hydrogen ions making things acidic, you've got the hydroxyl ions making things basic. If you mix them together, they just create water. So it neutralizes it. It gets rid of the acidic and the basic properties and just makes the whole thing neutral. When we talk about metals, if you want to check out the periodic table, which is in your book on page 8, you can also just look online for periodic tables. The one on page 8 is pretty good though. And it's color-coded, so it shows you what are metals and what are nonmetals. And like we said before, metals react with acids. They replace the hydrogen. And there's kind of a ranking of metals on how well they do this. And this is called the electrochemical series. So this is table 3 in your text. And it lists the metals by activity. So the higher the metal is on the list, the better it is at replacing hydrogen in an acid. So the ones on the top of the list are kind of the strongest. They're able to replace hydrogen in an acid the best. They can also replace those other metals that are below it. So if you could take a metal from the bottom of the list, put it in an acid, it replaces the hydrogen. It's now part of that salt. But if you take then a metal that's higher on the list, put it in the same solution, it'll kick out the lower metal and take its place. Okay, so the ones at the top are definitely stronger than the ones at the bottom. So many substances split apart into cations and anions when they're dissolved in water. This is called ionization. So a good simple example of this is table salt, sodium chloride. If you put it into water, it breaks apart into a sodium ion and a chlorine ion. And because these ions are charged, you've got positive sodium ions and negative chlorine ions. Now the solution is able to conduct electricity. So pure water itself that's perfectly pure H2O actually doesn't conduct electricity. But as we all know, or we all should know, you can get electrocuted in water pretty easily. It's because water has lots of ions floating around in it, from picked up from all over the place. So even water that seems like pure water, it's going to have lots of ions in it. So because there's these charged bits floating around, you got all these negative chlorine ions that can just float around and take electrical charge with them, it allows it to conduct. One use of this is electrolysis. So when you set up electrolysis, you've got a power source, let's say a battery that has a positive and negative end. You have an electrolyte. So an electrolyte is a solution that has ions in it, so it can conduct electricity. So salt water would be an example of an electrolyte. It's going to have positive and negative ions floating around in there. And then it's got these two electrodes. So electrode is just a chunk of metal that goes from one end of the power source into the electrolyte. And the negative one is called the cathode, and then the positive one is called the anode. So remember that you've got all these charges floating around, and charges are attracted to the opposite charges. So when you have this whole thing set up, the negative charges will flow from the cathode to the ionized solution into the anode. Okay, so that's pretty much electrolysis. It could be used for a couple different things, but this is how it works. You got negative charges going from the cathode through the electrolyte, which contains lots of ions, makes it able to move, and they're attracted to the anode. Assignments 8 and 9 talk about the periodic table. I'm not going to go over all of it because it's all kind of straightforward. It's just a lot of information. So it actually goes over all these groups that I have color-coded here, and it actually talks about each element in the group. Okay, so there's over 100 of them. We don't really have time to go over them all, and we don't really need to. It's not something that you need to memorize. Just know where to look for it in the book. So if it asks about a certain element and its properties, or it asks about a certain group and its properties, check out those pages. Okay, so they go through all the elements, and hopefully you can find the right one that you need. Assignment 11 is about organic chemistry. So that's the study of molecules that contain carbon. Okay, so it doesn't matter what else they contain. If they contain carbon, they're considered an organic molecule. So it talks about hydrocarbons because they're the simplest. They're molecules that are made up of just carbon and hydrogen. So you get carbon, it needs to form 4 bonds, so you get hydrogen around it. And it goes into talking about homologous series. So a homologous series of hydrocarbon would have similar structures, but only differ by adding a carbon atom and its hydrogens. So you got methane, which just has 1 carbon atom. If you add another one and the hydrogens that go with it, you get ethane. If you add another one and the hydrogens that go with it, you get propane. And this list can keep going and going. It gets longer. So that's just what we call a homologous series, where you just kind of add one thing and it keeps growing. So they have similar properties, but they're not exactly the same. Other homologous series in organic chemistry are made mostly of hydrogen and carbon, but there's also a functional group. So for example, just adding an OH to a simple hydrocarbon makes it an alcohol. So you get this other homologous series. So we got methyl alcohol, it only has 1 carbon, and it's got this functional group here. That's what makes it an alcohol. And then if you just add another carbon and its hydrogens, you keep this functional group. Now we have ethyl alcohol. You add another carbon, keep this functional group. Now we have propyl alcohol. And this list can also just keep going and going. So if you want to look at page 131 to 139, there's different organic molecules, different homologous series, and it kind of talks about the properties of each one and the structure of each one. So definitely check that out for your test. And at the end, it also kind of talks about these very general groups. So you've got carbohydrates, you've got aromatic compounds, plastics, things used as medicinals, which is kind of a wide-ranging group, and synthetic fibers, so things created artificially, but they're still organic chemicals. Um, these are shown on page 143 to 145. So if you see any questions asking about those, just be sure to go look those up. Okay, and that's all the time that we have for today. But if you have any questions, here are 3 different ways you can get in contact with an instructor.